If I can't picture it, I can't understand it. Albert Einstein. Welcome students. Today in Newton's laws of motion, we study dynamics of curvilinear translation. Actually, we are going to study dynamics of circular motion. Why? Because a curvilinear path or a curve may be assumed as if it is consisting of infinitely large number of infinitely small circular arcs or infinitely small line segments. Here in this picture, you can see a curvy road, and on the turn, one thing is very apparent, means very clearly visible that here is a motorcyclist, and on the turn it leans inside of the turn from vertical. One more thing, if you see very carefully, you can see this road on the turn has slope inward, means it is somewhat having a downward slope inside the curve. Actually, this kind of thing is called banking of roads on turn, and this banking is very dominantly visible on racing tracks where speeds are very high. When we analyze the banking of tracks, we see this banking angle depends on speed of the vehicles. But on highways, this speed is not very large, but on racing tracks, this speed is very large. So on racing tracks, this banking is apparently visible, we can see there. But on highway, you have to observe this banking very carefully. Now, before we start with dealing curvilinear translation or basically circular motion, let us revise few concepts from circular motion, what we have studied in kinematics. Actually, in kinematics, the angular velocity, centripetal acceleration, tangential acceleration, angular acceleration, all these ideas we have studied. Now, just we revise them and we simply enter how to apply Newton's law on circular motion, and that is called dynamics of circular motion. Tangential and normal components of acceleration. Actually, I am not going to revise the entire kinematics, only the important fact what we have to use here. Tangential and normal component of acceleration. What they are? Acceleration vector of a particle moving on a curvilinear path can be resolved into its normal and tangential components. In the figure, the acceleration vector and its tangential and normal components of car moving on a curved road are shown here. Just we see on a curvy road, that is in this way, a car is moving, and here you can see its velocity vector. Now its acceleration vector in some this way, and it has two components. One is parallel to velocity, means along the tangent, that is called tangential component, and one is perpendicular to path, that is called normal component. So this way we can see this is the an normal component acceleration, and this component is called a tau, the tangential component acceleration. And what they are actually doing here, normal component acceleration or centripetal acceleration. This component of acceleration accounts for change in direction of velocity vector, and its formula you know very well, just we revise it. An is equal to mod of an vector, and that is equal to omega v into v. And what we mean by omega of v? This omega is not the angular velocity of vehicle or the particle. It is angular velocity of the velocity vector, or you can see in other words, it is angular velocity of the radius of curvature. So that's why to denote it specifically, I am writing here a subscript omega of v, means it is more clearly apparent the angular velocity of velocity vector. Or we may write omega v square into rho, here rho is the radius of curvature. Or we can write here v square by rho, here rho is the radius of curvature of the path at this point. Here rho is the radius of curvature of the path, and omega v is the angular velocity of the velocity vector. Please take care of these things. Now let us discuss about tangential component, what it does. Tangential component of acceleration. This component of acceleration accounts for change in speed. It points along the velocity vector. It may point in the direction of velocity vector if speed is increasing, or if a tau is opposite to velocity vector, the speed is decreasing. So how we can write a tau? A tau is the magnitude of a tau vector, that is dv by t. Here you can see v is not vector, is magnitude, so it is rate of change in speed, or we can write here again v dv by ds. So sometimes we have to use this formula, sometimes we have to use this formula. So now it is complete revision of most important thing what we take from kinematics of circular motion. Now we discuss how we can apply Newton's law on circular motion, or you can say dynamics of curvilinear translation. While applying Newton's laws in curvilinear motion, the net force acting on the particle is usually resolved into its tangential and normal components. You can see here, we can take the same car, it is moving here with velocity v. So some of the forces may be acting on the car. Now here may be mg acting downward, means into the plane of figure, and normal reaction from the road acting upward, or here outward from the plane of figure. But these two forces will be equal, so cancel each. So we show only the net force, and the net force will be somewhat here because we have seen earlier the acceleration vector in this way. So this net force will produce accelerations, and what kind of acceleration? Tangential and normal. So we resolve the net force into two components, tangential component and normal component. So we call here summation Fn, means net normal component of force, and summation F tau means net tangential component of the force, or you can say tangential component of the net force, or you can call it normal component of the net force. And these two forces are responsible to provide both the acceleration components, tangential as well as normal. So here we resolve, here this is a normal direction, this is tangential axis. So the car is here, ma vector is here, so that is what? Man, and it is what? Ma tau. Now we can write both the equations. Here, instead of taking xy axis in circular motion, we usually take normal and tangential axis. And normal and tangential axis have their orientation pre-decided. Tangential is along tangent to the path, and normal is normal to the path. So here is no confusion in taking orientation of the coordinate axis. So what equation we can write here? Summation Fn is equal to Man. And Mn, here we can write description of An, this is v square by rho, or we can write omega square rho, m omega v square rho. Here what is omega v? Angular velocity, velocity vector. Similarly, second equation what we can write here? Summation F tau is equal to ma tau. So that is m dv by dt or m v dv by ds. Now you have to take care of one thing. But because usually the problems what you face in usual textbooks, in almost majority of the problem, only centripetal acceleration is there. There is no tangential acceleration. But in some few problems, there is tangential acceleration. So always take care of the tangential acceleration if it is present or not. And how you can judge? If speed is varying, there must be tangential acceleration. If speed is constant, there is no tangential acceleration. The normal component of the force is responsible for change in direction, whereas the tangential component for change in speed. I'm again specifying this thing. The normal component is for change in direction. It means if a particle of a body is moving in a curvilinear path, it must have normal component acceleration, but it may or may not have tangential component acceleration. When it will have tangential component? Only when its speed will change. But why it will always have normal component acceleration? Because it is moving on a curvilinear path, so its direction of velocity vector is continuously changing. So it must have a normal component acceleration, but tangential component it may or may not have. In circular motion, normal component of the force is usually called the centripetal force. When a particle moves with increasing speed, the net tangential force acts in the direction of motion, and when the particle moves with decreasing speed, the net tangential force acts opposite to direction of motion. So that is very common fact. Now, if you know these two things, how to resolve the forces along the normal direction and along the tangential direction, and expression for tangential acceleration and normal component acceleration, we can tackle any problems on curvilinear translation. Of course, for circle, the radius is known, and for curve, the radius or curvature of the point under consideration either must be specified or we will calculate with some other measure. And how we calculate radius or curvature, we have seen in kinematics in detail. So example 1. Now what I said that whatever we have revised till so far, with the help of these things, we can solve any problems on circular motion as well as on curvilinear translation. So let us start with a very simple example. In a free space, a man builds a small stone P of mass n with the help of a light string in a circle of radius r as shown in the figure. Establish the relation between the speed v of the stone and the tension developed in the string. So what the situation here? The man is holding the thread at this end and hit the stone. The man is whirling the stone on the circular path, and how this motion has been established. Here, please take care. You might be thinking that this man is shaking this hand in this way and this particle is moving. But this is not the situation. If this man is moving this hand like that to move this here, it means this center is not stationary. How this motion has been established? Actually, the man holds the string here with the other hand. He makes the string horizontal and impart this velocity. And in free space, there is no resistance. So this particle will keep on moving on the circular path with constant velocity, as well as the string will remain horizontal because there is no gravity to pull this stone downward. Now, this is what logical analysis of the process. Actually, what I am stressing while dealing any problem, try to understand the process involved in the problem. If you can understand the process clearly, you can write the necessary equation very easily. So what we can think? In free space, no force other than the tension acts on the stone. Thus, the string remains horizontal and the tension developed provides the necessary centripetal force. Here drag is not present. Thus the stone moves with a constant speed. Therefore, the tension does not have any component tangential to the path. So here speed is constant, so there is no need of any tangential force. So tension will be normal to the path. Now we can apply Newton's law and write the basic equation. NLM, an inertial frame. We are using inertial frame. Actually, I do not recommend unnecessary to use a non-inertial frame. So here, so we consider the particle at some time here. So we apply the only force tension T and equal to kinetic diagram. That is here MAN, that is only normal component acceleration is there. So what we can write equation? Summation Fn is equal to Man. That is T is equal to V square by R. We can substitute the expression for N, V square by R. Here R is the radius. And from here, we can find the desired result, that is the expression for the tension T. Because here An is equal to V square by rho, and rho is the radius of curvature. Here for circle, this rho assumes the value capital R. So that was very simple problem. But here some students prefer to use a non-inertial frame. Actually, large number of non-inertial frames may be possible, but which we have to prefer? Here we can prefer two reference frames which are non-inertial. One you can assume with its origin at the center of the path and rotating with the same angular velocity as the particle is moving on the circular path. Or you can take another reference frame that is non-rotating, but its origin is at the particle or at the stone and that is moving together with the stone. So that reference frame has the same acceleration as the particle has. And in this reference frame, the particle is assumed or is apparently visible in equilibrium. Of course, it is not truly in equilibrium, but it will assume stationary. So we prefer this reference frame. So here, what we can take here? Here a non-inertial frame that moves together with the stone without rotation is used, as this non-inertial frame moves together with the stone, its acceleration is equal to that of the stone. Thus, a pseudo force has to assume acting in addition to the tension force or tension of the string. So, particularly this kind of non-inertial frame, if you choose in circular motion, you will find more simplicity, and without any ambiguity you can take decision. So, what we can take here? So, here this force and the origin of the reference frame is attached here. So this reference frame is moving on this path, so it has the same acceleration. So here we have to apply pseudo force opposite to acceleration of the reference frame. Reference frame acceleration is towards on that side, so and equal to normal compound acceleration of the particle. So we assume here pseudo force man outward, and in this reference frame this particle is observed stationary. So what equation is? T is equal to man. Summation F and RP. R means real forces and pseudo forces equal to 0. So what you can write here? T minus Man equal to 0. So T is equal to Man. Now we can substitute the expression for An, that is V square by R. So we got the same result. Now you can see both the approach using inertial frame or using a special non-inertial frame are equivalently valid. But what I personally recommend, try to use or try to prefer to use an inertial frame always, until unless it is not necessary. Now let us come on the next example. Example 2. A small ball is suspended with an inextensible light thread from a fixed support on the ceiling. The ball is pulled aside and given a horizontal velocity perpendicular to the thread. As a result, the ball begins to move in a horizontal circle and the thread begins to sweep a cone. This is called a conical pendulum. So how the situation is? This way. If the ball was suspended, the thread were vertical, but this ball is pulled aside, keeping the thread straight. Now it is given a velocity. That velocity is horizontal as well as perpendicular to the thread. So in this way, the ball will begin to move on a horizontal circle. If there is no air drag, speed of the ball will remain constant, and this circular motion is continuing. This device or this kind of setup is called a conical pendulum. Now what we have to calculate? Denoting mass of the ball by m, length of the thread by L, and half angle of the cone by theta, deduce suitable expression for the speed of the ball and period of its circular motion. Now, as we are doing in all the problems, we first try to visualize the process, and what we visualize, let's just document it. So what we do, see, forces acting on the ball are its weight mg and tension T of the thread. These forces together provide the necessary centripetal force to the ball to move on a horizontal circle of radius L sine theta. None of the forces has any component along a tangent to the circle. Hence, the ball moves on the circle with a constant speed. Now you can see what is the radius. So if this length is L, this angle theta, clearly you can see from trigonometry it will be L sine theta. So the ball will move on the radius of L sine theta and center is here. Now there is no air drag, so the speed of the ball will remain constant, and again it is also clearly visible. So tension T acting along thread and mg, none of these forces has any component along the circular tangent. So speed of the ball will remain constant. Now if we can think all these things, the problem is over. Only we have to write mathematical equation, and for this we have to select a reference frame, and as usual we will prefer to use an inertial reference frame. So let us take a ground frame or laboratory frame as inertial frame, NLM from the laboratory frame, inertial frame. Sometimes it is called ground frame also. So what situation is? For clear visualization, we assume the ball at this point. So this angle theta, this length is L, so this is what radius is L sine theta. This is center. Now forces acting are mg downward and tension T along the thread this way. And we draw the kinetic diagram, and it has only normal compound acceleration towards center. So we draw this effective force Man. Now we have to assume a coordinate axis. Here, normal direction is this way, but this direction is what? Another direction. It is not tangential. So what we call it y. Here, tangential direction is perpendicular to the plane of figure, but none of the vector are in tangential direction, so no need to show the tangential axis. So here the coordinate axis, y vertical, and x is equivalent to the normal axis. And accordingly, we have to do the components of the tier only. So what the components? Here, this length will denote the vertical component and this length will denote the horizontal component or towards the center component or the normal component. So this will be t cos theta and this will be t sin theta. You can very easily write. Now the first equation, summation Fn is equal to Man, we can write. Summation Fn is equal to Man. So in the normal direction, there is only one force, this component. So t sin theta will be Man, and instead of An we can write here v square by radius. Radius is L sin theta. Equation 1. And second equation we write for this y direction or vertical direction. In vertical direction, there is no acceleration. So summation Fy will be 0. Summation Fy will be 0. So what we have? T cos theta is equal to mg. Now by using these two equations, we can find all the required quantities. Let us see how we perform the calculation. And for the purpose, I am writing again the same equation. So first equation, t sin theta is equal to mv square by L sin theta. And second equation was t cos theta is equal to mg, second equation. Now what we can do? Just we can take a ratio of their LHS, a ratio of RHS and equate them. You will find speed. From the equation 1 and 2, we get the speed of the ball. That is v is equal to gl sin theta tan theta. Not difficult calculation, you can do it. And for period, what we do? We know the particle is moving on the circular path with constant speed. So for period, what we can do? We can calculate the circumference. We know the radius is L sin theta. So what will be circumference? 2 pi L sin theta upon this speed. As the ball moves with this constant speed on the circular path of radius L sin theta, thus period of the circular motion can be obtained by dividing the circumference of the circular path by the speed. So this is not a difficult task. You can verify this answer. So t is equal to 2 pi L sin theta upon g tan theta. So in this way, that is a period of the circular motion, and that is speed of the conical pendulum. So this conical pendulum is again a very important thing, and sometimes in so many examinations, problems based on conical pendulum are asked, and you can see how simple the analysis was. Now let us come on the next example. Example 3. A boy stands on a horizontal platform inside a cylindrical rotor with no gap between his back and the inner surface of the rotor. The rotor can be rotated about its vertical axis of symmetry. The angular speed of the rotor is gradually increased. Find the minimum angular speed at which, if the platform on which the boy is standing is removed, the boy should not fall. So this is situation you can see in diagram. Here this structure has been assumed to be removed. Actually it is not removed, but it is imagined to be removed. So you can see the boy. The boy is standing with his back on the inner wall, and here is the platform on which the boy is standing. And in this way, the rotor, this cylindrical container, or you can say rotor, is being rotated. And now its angular velocity is increased gradually. Gradually means at a very infinitely small rate. It means its angular acceleration will be 0. If angular acceleration is 0, what we can think? The boy will have no tangential acceleration. Or tangential acceleration we can ignore. So what we can see? All the forces acting on it must be providing the only centripetal force, and the problem is over. Now you can see again the centripetal force must be towards center. So that force can be created only by normal reaction from the wall. And if there is normal reaction from the wall, and if this platform is removed, the gravity, weight of the ball will, the boy will pull it downward. So there will be a static friction which will act upward, and this force of static friction will balance the weight of the boy. So this is the qualitative analysis of the problem. And what is remaining now? Only what we have thought qualitatively, we have to express it mathematically. Denote the coefficient of static friction by mu s, radius of the rotor by r, and acceleration of the free fall by g. So we have to find this, and these are the information given. So what we have qualitatively thought, let's document it first. As the rotor rotates at angular speed omega, the buoy moves on a circular path of radius r with a speed v is equal to omega r. Since angular speed is increased gradually, the angular acceleration can be ignored and hence the tangential acceleration of the buoy. Thus, the buoy has a centripetal acceleration only, or that is omega square r. And this is provided by the normal reaction n applied by the wall of the rotor. The weight of the buoy is balanced by the force of static friction, and that certainly will act upward. Now we can only think we have to make FBD, show all the forces and equate to kinetic diagram. And of course, it is obvious to use a laboratory frame or ground frame, that is inertial. So all these forces are shown in the following figure, where the buoy is shown schematically by a rectangular box of mass m. Actually, when you are solving the problem, I will not recommend you to draw a buoy, just show it by schematically by a rectangular box like that. So what are the forces acting on it? The normal action towards center here, and mg, and this static friction. So this static friction will balance mg, and for the static friction we must know the n, and that we can be obtained by applying Newton's law. Let us see how we can apply Newton's law. NLM from the ground frame, inertial frame. So FBD we have seen. So again I am drawing the free body diagram. So normal force mg, and this is static friction, and this will, all these forces, the resultant will provide the necessary centripetal force. So here this MAN, and so again we have to coordinate axis. This is normal direction, and this we call vertical direction, y-axis, because tangential direction will be again perpendicular to the plane of figure. So here y-axis and x is equivalent to the normal axis. So summation Fn is equal to Man. So what we can write here? N is equal to m omega square r, because An we write omega square r, because here velocity is not given, omega is given. So N we have calculated. Now we can calculate force of static friction, where actually here again given, that is An is omega square r. Force of static friction, that is Fs, is less than or equal to mu s into n. This is limiting friction. So what we can write here? Fs is less than or equal to m omega square r, because we have substituted value of n here. So we have obtained static friction. The only thing is what? We have to equate this static friction with mg. So summation Fy equal to 0. So Fs is equal to mg. If we substitute this value of Fs, what we get? Substituting expression of the static friction, we get mu s m omega square r must be greater than or equal to mg. So from here what we get? Omega must be greater than or equal to under root g upon mu s into r. So this is the angular velocity. And what is the minimum angular velocity? So omega minimum is equal to under root g upon mu s into r. So in this way, we have calculated the minimum angular velocity of the rotor so that the buoy will not fall. So again, these examples are very simple examples. Let us take the next example. Example 4. A motorcyclist driving on circular path of radius r on the horizontal ground increases his speed at a constant rate. The coefficient of static and kinetic frictions between the tires and the ground are mu s and mu k. Write an expression for speed when tangential acceleration is a tau. Actually, now till so far what example we have taken, there were no tangential acceleration. Now in the first problem we are considering the tangential acceleration. So we can think first qualitatively. The forces acting on the motorcyclist, weight, normal direction, both these forces are in vertical direction and they will balance each other. So from here we can find what is the value of normal direction. Now once normal direction we have calculated, that is equal to total weight of the motorcyclist and motorcycle, we can estimate the static friction. What it will be? That is static friction will be greater than or will be smaller than or equal to mu s into n is what? Total weight. Now tangential action is also there. So this static friction acting along the ground in a horizontal direction will provide both these acceleration, the normal component acceleration and tangential. And one more thing is what? Mg was balanced by n. So when we are analyzing the problem, there is no need to show the vertical forces, only show the horizontal forces. What? The frictional force and its component, the providing the centripetal force and the tangential. So we draw a top view of the diagram. Now let us proceed here. The motorcyclist and the motorcycle always move together. Hence, they can be assumed to behave as a composite rigid body of mass equal to that of the motorcycle and the motorcycle. Let the mass of this composite body be m. The external forces acting on it are its weight mg, the force of normal reaction and the force of static friction Fs on the tires from the ground. Please take care. Whether any vehicle when moves, it is desired that its wheel will not slip. So it is always desired that static friction should act. So what we are assuming here, static friction. The composite body has no acceleration in the vertical direction. Therefore, the normal reaction balances the weight. So normal reaction will be equal to the weight of the body. So what we can write here, n is equal to mg. So this is an important equation. So from where we can write the static friction, Fs is less than or equal to mu s mg, and we call equation 1. Now we can apply Newton's law, and to apply Newton's law, only see the top view. What? We have to show the normal component and tangential component. On the circular path, the only external force in the horizontal plane is the force of static friction, which is responsible to provide the body necessary centripetal as well as the tangential acceleration. These conditions are shown in the figure, where forces in vertical directions are not shown. So in this way you can see we can assume the motorcycle here by a particle. So this is the force of static friction. We are assuming it not toward the normal at some angle. So we are assuming the motorcycle is moving this way. So what we can see, the kinetic diagram, what ma. So this will be what component ma tau and man. Accordingly, we can orient the coordinate axis. So here the coordinate axis, the tangential direction and normal. So accordingly, we do the component of static friction. So this way, so this is what F tau and this is what Fn. So F tau is the tangential component of the static friction and Fn is the normal component of the static friction. Now we are in a position to write equation. So to write equation, which reference frame should we use? NLM from the ground frame, inertial frame. So again, I am redrawing the diagrams. FBD, Fs equal to ma and its component ma tau and man, this man and ma tau, and again component of this s, tangential component and normal component. This is what Fn, the normal component of friction force, and that is what the tangential component of the friction force. So what equation? Summation Fn is equal to man. What it gives? Fn is equal to mv square by r, and F tau is equal to ma tau, that is summation. So what we can here, F tau is equal to ma tau. Now what we can see, these two forces Fn and F tau are the rectangular component of static friction. So if we square them and 8, we get this one. So what we are doing the same thing, f tau square plus fn square is equal to fs square. So we substitute these values here. So from these relations or results and the equation 1, what we obtained earlier, what we get, mv square by r, that is whole square of this f plus this ma tau. Actually, this is what square of this fn square, and for f tau square, this ma tau square, and is less than or is equal to mu s mg, that is what square. Now by simplifying this, we can write v is less than or equal to r square mu s g square minus a tau square, that is whole power 1 by 4, because you can see here that is a power 4, so it will be 1 by 4. So in this way, we have calculated the speed of the motorcyclist. So this is what a first example in which tangential acceleration came into picture. So in this way, whenever there is tangential acceleration, you can account it by this way. Now let us come on the next example. Example 5. A particle of mass m is suspended with the help of an inextensible light thread of length L from a fixed point O. When the particle is at rest vertically below the point O or point of suspension, it is given a horizontal velocity v0 as shown in the figure. So that was situation. Here this particle was suspended from this fixed point O with the help of a light thread of length L, that of course it is inextensible, and it is given a horizontal velocity in this way. If this velocity is given, depending on the magnitude of velocity, several conditions may happen. If the velocity is very small, this particle will oscillate. If this velocity is very large, this particle will complete the loop, and for some intermediate value, this particle will leave the circle. So let us analyze few things. Part A, write expression for the speed of the particle and the tension in the thread when the thread makes an angle theta from the lowest position. Assume that the particle always remains on the circular path. So what we do, we want to write expression for tension in speed when this thread makes angle theta. So again, we have to see here all the forces. As the thread will give here, the tension will act towards the point O and mg is here. Now you can see this T will not have any component along the tangent, but mg will have component. So it will provide a tangential acceleration. So here tangential acceleration is there. Again, of course, the particle has velocity, so it will have the normal component acceleration also. Consider the particle at an angular position theta moving with a speed v shown in the figure. The forces acting on it are its weight and tension in the thread, which are responsible to provide the centripetal and tangential accelerations. So what we think or thought, the tension and mg, these are the two only external forces. So these two forces must be responsible to provide the tangential acceleration as well as the normal acceleration. And how they provide, let us see. For that, we have to apply the Newton's law, and we use again laboratory frame or ground frame as an inertial frame. NLM from the ground frame, inertial frame. So we assume the ball to be at some angular position theta and show all the forces. So here the initial position and we are assuming ball here. So forces acting are mg downward and tension T. These are two forces, and we show what the kinetic diagram. So in kinetic diagram, we show the MAN on this direction and MA tau. MAN and MA tau. Why I'm showing MA tau in this direction? Because we know very from common sense, as the particle move away from this position, its speed will decrease. So tangential acceleration will be opposite to velocity. Again, if the particle were coming down, its speed will increase. So again, tangential acceleration will be in the same direction. So whatever the case is, tangential acceleration will be in this direction. Now we can orient the coordinate axis. So tangential direction and normal direction. So according to this coordinate axis, we have to resolve only this vector t into its component or mg into components. You can see we have to resolve only mg into its component. So in this way, we can do the mg. So this angle is theta. This angle will also be theta. So this component will be what? Mg cos theta. and this component will be mg sine theta. Now we can write both the equations. One equation is summation fn is equal to mn, and second equation is summation f tau is equal to m tau. So let us first write summation fn is equal to mn, and for normal direction we can see t minus mg cos theta is equal to mn, and for an we can replace v square by l because l is the radius of the path. So t minus mg cos theta is equal to mv square by l. So equation number 1. Now we can write for tangential direction summation f tau is equal to ma tau. So for summation f tau we are having only this component. So mg sine theta will be equal to ma tau. So mg sine theta will be equal to ma tau, and from where we can write a tau is equal to g sine theta. So this is second equation. Now for the further analysis we have to use only these two equations. To find speed, consider the tangential acceleration. So the tangential acceleration is function of the angular position theta. Thus what we can write here, a tau is equal to v dv by ds, and for ds we can write l d theta in infinitely small arc. So a tau is equal to minus v dv by l d theta. Why minus? Because a tau is opposite to velocity here. So the minus sign is due to the fact as theta increases, that is particle moves upwards, v decreases. So in this way we have minus sign. So what we can write here? Now from equation 2 we get v dv by l d theta is equal to minus g sine theta. We have shifted minus sign from here to that side. Now what we can write here? v dv is equal to gl sine theta theta, and we integrate this v dv from v naught to v, and minus gl we can take outside of integration, and from 0 to theta. What does it mean? When theta is 0, speed was v naught. When angle is theta, we are assuming speed v, and this speed v we are calculating. So the calculations are very simple. What we can write here? V is equal to v naught square minus 2gl, 1 minus cos theta. So that third equation is the expression for desired speed at any angular position theta. Now to find tension, this expression of v will substitute in equation 1. To find expression for the tension in the thread, substitute this expression for speed in equation 1, and we can find tension T. T is equal to mv square by L, mv naught square by L minus mg 2 minus 3 cos theta, and that is equation number 4. I am leaving you the calculation. The calculation are quite simple. So in this way we obtain expression for speed at any angular position and tension thread at any angular position. B part. What should be the minimum speed at the highest point of the circular path? So for highest point, let us consider what is happening at the highest point. At the highest point, speed of the particle is the minimum one. So tangential acceleration is 0. Thus, no force acts in the tangential direction. So at the highest point, you can see speed will be minimum. So if any variable is minimum, its the derivative is 0. So at the highest point, derivative speed will be 0. So there is no tangential acceleration. So tension T and mg both will act downward. Now we are in a position to apply Newton's law. So NLM from the ground frame or inertial frame. So we can see all the forces acting here. That is, we are assuming the ball at the highest point, and we are assuming some speed. And let us see what will be the minimum value of this speed be. So mg will act downward and tension T. And the kinetic diagram, that will be MAN. So here MAN, and what will be N? V square by L. So what we can write equation only for normal component, because there is no tangential component. So this normal direction, and that is tangential direction. So summation Fn is equal to Man. So what you can write here? Mg plus T is equal to Man, or T plus Mg is equal to Man. And for An we can write V square by L. So T plus Mg is equal to Mv square by L. Now from this equation, the things are very clear. Mg is constant, so for different value of v, the t will be different, and for minimum value of v, t should be 0. And in this way, we can calculate the minimum speed at the highest point. For the speed at the highest point to be minimum, tension must be 0. Therefore, we have this. If you equate to 0, we can find minimum speed at top point. It will be root GL, because this will be 0, m will cancel. So v square will be equal to GL. So v is equal to what? Root GL. So that is what minimum speed at the highest point. What should be the minimum speed v naught min be given to the particle at the lowest point, so that the particle completes the circular loop? It means now we have to explore how much minimum speed v naught min should be given to the particle at the lowest point, so that it will complete the vertical loop or circular loop. For that, what we know, one thing we have calculated, the speed at the highest point minimum is what? Root GL. So how we can think qualitatively about situation? The equation 3 obtained in the first part gives speed v at any angular position theta. For reference, the equation 3 is rewritten here. Again, what is equation 3? V is equal to v naught square minus 2gl 1 minus cos theta. And what is this equation shows? One thing. This equation shows that smaller is the speed given at the lowest point, smaller is the speed at any angular position theta. It means how much, if you make it smaller, this speed will become smaller. So what we can think? For minimum speed at the lowest point, we can use the minimum speed at the highest point, and angular position theta is equal to 180. If we substitute these two values here, we get the v naught min. Thus, by substituting the expression of minimum speed at the highest point, what is that? V min is equal to root GL sine and theta is equal to 180 degree. In this equation, we can find the minimum speed v naught min given to the particle at the lowest point, so that the particle completes a circular loop. Now you can think here what this equation suggests. For smaller is the value of v naught, smaller is the value of v at any angular position theta. So to complete the vertical loop, we know the minimum speed at the highest point is root GL. So what we can do? The minimum speed at the highest point means theta is equal to 180. If we substitute in this equation, we can find minimum value of v naught. So let us do it. So this is what? Root GL, that is v naught min square minus 2gl 1 minus cos 180 degree, and by simplifying this you can get here v naught min is equal to root 5gl. So this is a very important relation. Actually, this vertical circular motion is a very important problem for almost all the examination. And here, what the parts we have done here, if you can reproduce these parts, you can solve any problem on this vertical circular motion. Now let us come on the next example. Example 6. A cyclist, while executing a turn, has to lean from the vertical towards the center of the turn. As far as speed and radius of the curvature of the turn remains uniform, the lean angle remains constant. So that is very fact we have seen on the first figure on the introductions. And again, it is a common experience from you, and you also have rode your cycle or motorcycle. So when you're turning your cycle or bike, leans inside the turn by some angle. And one more thing, you can observe that higher is your speed, more is the leaning angle. Again, one thing what we can see here, what is given here, as far as speed and radius of curvature of the turn remains uniform, the lean angle remains constant. So what we have to calculate here, a cyclist executes a turn of radius r with a uniform speed v on a road where coefficient of static friction is μs. Find suitable expression for the maximum uniform speed with which can the cyclist execute the turn and the corresponding lean angle. So what you have to calculate on a turn, what can be the maximum safe speed cycle and what will be its lean angle. So what we have to think, say here, we are assuming a cyclist on the turn and it is leaning from the vertical by an angle theta, and here is center of mass of the cyclist as well as cycle, because here cyclist and cycle will move together, so we can again assume them as a composite body. Now this is mass center of this composite body, and here radius r is the radius of the path on which mass center is moving. This r is not radius of this the track which wheels are following, and here p is the point of contact of the wheel with the road. So what we can think here, in the figure the cyclist is shown leaning at angle theta from the vertical while executing a turn. One thing, the cyclist and his bicycle both move with the same velocity and acceleration, thus can be treated like a composite rigid body. And what I already mentioned, that this C is the mass center of this composite rigid body. And what you can further think, the distance of the mass center C of the composite rigid body from the point of contact P with the road is so small that radius of curvature of the path of the mass center remains almost equal to that of the path traced by the wheel on the road. Actually, as compared to this radius, this length is very small. What actually radius of the road are about 10 meters, 8 meter, or even more. So about 10 or 8 meter, this height is hardly less than 1 meter or 1 meter. So as compared to 10 meter or higher radius, 1 meter is negligible. Again, this angle is very small, say 10 degree, 15 degree, 20 degree, not and even 30 degree. For that, this distance will be even smaller than 1 meter. So this distance we can neglect as compared to this radius. So if you say radius of path, it means what radius you have to consider? Radius on which mass center is moving. So that is very important thing to consider. Now, after thinking all these things, we are in a position to apply Newton's laws. So if you think about Newton's law, what the forces are acting, weight mg downward here, normal direction, and of course it has centripetal force toward this, so the static friction will act in this direction. Now let's apply Newton's law. NLM on the composite body from the ground frame, inertial frame. So say this is cyclist, forces before we show the forces, let us show the lean angle, and this at mass center we show mg. Here mg is the total weight of the composite body and c is the mass center of the composite body, and here is the normal direction at point of contact P. Now here is the force of static friction, so that will be less than or equal to mu s into n, and mu s into n is the limiting friction. Now all the forces we have shown, only thing is what we have to show the kinetic diagram, so equal to this way, and at C what we show mv square by r, that is normal component acceleration. We have substitute value, instead of writing mn, what we written directly mv square by r. Now the coordinate axis here, y is vertical and x is equal to equivalent to n. So we can write summation fn is equal to mn and summation fy is equal to my. So we first write summation fy is equal to may, and in y direction the cyclist has no acceleration, so it will be 0. So what it gives, n is equal to mg. One thing, and from here we can write force of static friction. Frictional force between the wheels and the road, what fs must be less than or equal to mu s into n, and if you substitute value of n, what you get, mu s into mg. So fs is less than or equal to mu s into n, what it gives, fs is less than or equal to mu s into mg. So that is force of static friction. Now we can write equation what, summation fn is equal to man, so that will give us fs is equal to mv square by r. So fs is equal to mv square by r. Now we substitute value of fs, so what we get here, substituting expression for the frictional force, we get, that is v is less than or equal to mu s cr. So what we have here, if we substitute this inequality, so we get here mv square by r is less than or equal to mu s mg, and by solving what we get here, v should be less than or equal to mu s cr. So what can be the maximum safe speed? You can see here mu s cr. Otherwise, if we are having speed lesser than this, it is always safe. But if we exceed the speed of that, this force of static friction will cross its limiting value and the cycle will slide outward, and this phenomenon is called skidding of the vehicle. So in this way, what is the safe speed? You can see mu s cr. To find the lean angle, rotational equilibrium of the cyclist has to be taken under consideration. Okay, this is very important thing. Actually, lean angle, I have seen in some of the textbook, they are calculating with the help of Newton's law, but it cannot be calculated with the help of Newton's law. Just they are doing some mathematical manipulation. Actually, to calculate lean angle, you have to apply conditions of rotational equilibrium. But till so far, we have not studied conditions of rotational equilibrium. Still, we can use a very common idea. And that is what idea? If a rigid body is in rotational equilibrium, it is not rotating and only two forces are acting. These two forces must be collinear. And if the body is in equilibrium, these two forces must be equal and opposite. You can have an experience. Take a book on the table and start pushing the book from your fingers from both sides. And if your forces are collinear, the book will not rotate. If your fingers are not collinear, means the forces are not collinear, the book will start rotating. So to stop rotation, what you do? Both the forces must be collinear. That is what here again a very common sense experience, and we'll use it. We have not studied the conditions of rotational equilibrium till so far. Still, by using the following very common fact, we can easily deduce the expression for the lean angle. And what is the common fact? If a rigid body is in translational as well as rotational equilibrium under the action of two forces, the forces must be equal in magnitude, opposite in direction, and collinear. Here, equality of magnitude and opposite of direction. This is requirement for translational equilibrium. And for rotational equilibrium, these two forces must be exactly facing each other. Means they must be collinear. Now we can think. On the cyclist, you will see there are three forces. And we have to resolve these three forces into what? Two forces. Not, again there is what? A MAN. So if we use the non-inertial frame, here is a need of non-inertial frame. So in non-inertial frame, a pseudo force will be applied on C that will what? MN outward. So resultant of mg and MN will be one force. A resultant friction and normal reaction will be another force, that is known as total contact force. Now you can see only two forces are acting on the cyclist. What? The resultant of mg and MN and the total contact force. And these two forces must be collinear. And we will use this condition here. How we can use this? Consider a non-inertial frame. That is a non-rotating frame attached with the mass center of the composite body. In this frame, we can consider that only two forces are acting on the body, that are the total contact force at the point of contact P and the net resultant of weight and the centrifugal force as shown in the figure. How the forces are acting, see here, the cyclist and lean angle theta. So here what forces? mg and n, and this what mv square by r, mn pseudo force, it will be act outward, and the frictional force this. Now resultant of these two forces will be what? This r. We show the total contact force this way, and the resultant of these two forces, and these forces must be collinear. So r must be this resultant of this force. These two forces must act along this line because r is also acting along this line. So this is, So that is what resultant of these two forces. Now you can see very easily this angle is theta, this angle is also theta. So from here what you can write here, mv square by r is equal to this. So mv square by r is equal to mg tan theta. So mv square by r is equal to mg tan theta. From here you can write directly what is angle theta. So theta is equal to, or tan theta is equal to v square by rg. So what is the theta? Tan inverse v square by rg. Now a care has to be taken. The maximum lean angle is equal to the angle of static friction. Actually, lean angle will always be equal to or smaller than the angle of static friction. It cannot exceed the angle of static friction. So that was a very important fact. We have used it without studying rotational equilibrium, just by a very common fact. And I will ask you to revise this common fact very carefully. Now let us come on the next example. Example 7. A two-wheeler can lean while executing a turn, but a four-wheeler cannot. Find expression for allowable speed of a four-wheeler on a turn of horizontal road. Denote radius of the turn by r, coefficient of static friction between the by mu s, and acceleration due to gravity by g. So what is this? We can reduce from here. On a turn, if the turn is not banked, say horizontal road. On unbanked turn, if a two-wheeler is going, it can lean and it can achieve the that is by friction, that is required centripetal force. But on on this horizontal road, a four-wheeler cannot lean. So it can achieve its centripetal force by the force of static friction only. So let us analyze this. Normal reaction on all the four wheels are not usually equal. In addition to this, friction necessary to provide the centripetal acceleration is created at the steered wheel only. The above two facts can only be taken into consideration after the study of rotational motion. So this is again a very important thing. It is a very common idea or simple idea that loading of the vehicle cannot be equal on the four wheels. It may have unequal loading on the four wheels. So on the four wheels, normal reactions may be unequal. One more thing you will study in rotational motion, that is, when the vehicle is steered, the necessary friction to provide centripetal force is available only on the steered wheel. So to calculate friction, we cannot, for centripetal force, we cannot use the entire mu s mg. It will be less than mu s mg, because on the front wheel, it will be partially loaded, because it will have some normal action on the front wheels, and there will be some normal action on the rear wheel also, and all these normal action will balance the weight. So here, this fact, of course, very important, but this we can analyze only rotation motion. So what important assumption can we make? Let us see here. Here, for the sake of simplicity, we assume that all the load of the car is on its front wheels that are being steered. The same assumption has been made for the cyclist too. Actually, what is being assumed here in this analysis, what we are going to do, that all the load of the vehicle is on the front wheel which is being steered. And the same assumptions we have made in the case of cyclist, but at that time I have not told you it. But please take care of, because this idea can be raised in rotational motion. So NLM of for the car from the ground frame, that is inertial frame. So we can show all the forces. We will show only the front wheels. So here this radius of this center of mass path. So that is mg, that is vector is acting at center mass of the car, and here n1 and this n2. Again, on these two front wheel, normal action may not be equal. So I am showing them unequal. So here will be the force of static friction Fs1, and here the force of static friction Fs2. and fs1 will be equal to or smaller than mu s into n1, and fs2 will be equal to or smaller than mu s into n2. And the kinetic diagram, that is mv square by r. I'm not again showing the car here, so just show the normal component of effective force. So coordinate axis, that is y vertical and x is equal to normal. So what we can write first, summation fy equal to 0, because the car has no acceleration in the vertical direction. So what we can write here, n1 plus n2 is equal to mg. This is one equation. And summation fn is equal to man. So in normal direction there are two forces. So what we can write here, fs1 plus fs2 is equal to mv square by r. fs1 plus fs2 is equal to mv square by r. Now we know that fs1 is smaller than or equal to mu s into n1, and fs2 is smaller than or equal to mu s into n2. We will use these values here. So fs1 is less than or equal to mu s into n1, and fs2 is less than or equal to mu s into n2. From these equations we get, you substitute this, what you get here? Here, if you mv square by r will be less than or equal to mu s into n1 plus n2, and n1 plus n2 is equal to mg. Now we can easily write the answer. So v is less than or equal to mu s here, and this speed or expression is the same what we have obtained for cyclist. So what cyclist has achieved this by leaning. Actually leaning was for other factor. It was just to maintain the cyclist in rotational equilibrium. Leaning there was not providing any centripetal force. In here again that centripetal force we are getting from friction, and no leaning is required. Now here from here we can have some very important idea, and we try to estimate this speed limit for some reasonable value of mu s, g and r. Reasonable estimate. Reasonable means very useful value. So r is about 10 meters. So for in the city or some you can say 10 meter track radius is almost very common, and mu s is 0.64. This 0.64 I'm using just to simplify calculation, and this mu s coefficient static friction between tire and the road is about 0.7, 0.8, and value of g I am taking here 10 meter per second square. If you substitute these values, so mu s into g into r, so 0.64 into 10 into 10, what you get? 64, and square root of this is 8. So v is less than or equal to 8 meter per second. Let us convert into kilometer per hour. So it will be less than or equal to 28.8 kilometer per hour. It is very easy to calculate, and just we have approximated by 30. So v is less than or equal to 30 kilometer per hour. Now we are coming on banking of track, and for this 30 kilometer per hour speed is very important. You might have seen on the roadside so many times 30, 30, 30 number written. So that is speed limit near the turn, and this speed limit is not very high. Actually, if you're driving in a city, that speed is reasonably good, but on highway that speed is very small. So if someone is driving on the highway and a turn comes, so the driver has to reduce the speed to 30. But if it does not reduce the speed to 30, the vehicle may slide or it will skid outside. So that is undesirable or dangerous event. So what we can think here, the speed limit 30 km per hour as estimated is the maximum possible speed of a four-wheeler that can have on a flat turn. The friction coefficient and radius of the turn are assumed to have their typical practical values. Certainly, the speed is much smaller and the driver has to take utmost care to avoid any mishappening unless some special measure are taken to increase this speed limit on the turns. Actually, what the driver has to do whenever turns comes or whenever he arrives on a turn, he has to reduce his speed below 30 so that he can negotiate the turn safely. But if he does not reduce the speed below 30, there may be an accident. So if we can increase the speed limit, then it will be a desirable thing. So some special measure has been taken to increase the speed. And what the special measure? Actually, we have to increase the real forces available to provide the centripetal force. For that, the banking has been done. You can see on banking, the normal reaction will be tilted. So some component of normal reaction will be available for the centripetal force. Of course, you can think the friction has been reduced because now only the horizontal component friction will be available. But reduction in the horizontal component friction is smaller than the available horizontal component of normal reaction. And we will see further by analysis. So that's why banking has been done. One of the usual methods adopted for the purpose is to make the road inclined to have a transverse downslope towards the inside of the curve, as shown in the figure. This measure is known as banking of roads. This way. Now you can see it on very clearly, the road is sloping. Now you can see one thing. Here slope is very little and here slope is larger. So this road is designed for variable speed. If speed is very low, the car is moving like that. For higher speed, the car will move on this lane. For more higher speed, the car will move on this lane. This lane, because for higher speed there is more banking is available. The banking of roads can easily be observed at the turns on the highways and railway tracks. If you can see the highway, actually in cities, this banking will not be visible because in cities you'll find several times marking 30 km per hour speed limit. So you are want to have speed limit below that. And one more thing, in cities or town area, the traffic condition will not allow us to have speed more than that on turns. But on highway, we have to drive at a very high speed. So banking is available here. So when you go on some highway and see the turn, and you will observe the banking as I have shown you in the first picture. And again, this banking will be very, very clearly visible on the racing tracks. Now, in the further example, we try to analyze this banking. Example 8. Angle of banking theta for a curve is so decided that a four-wheeler can pass the curve with a specified speed v0 without any need of friction. Find the angle of banking in terms of the radius r, the specified speed v0, and acceleration due to gravity g. Actually, angle of banking is decided for a particular speed if there is no friction. Actually, this kind of adverse condition may happen on the highway. Say, suppose it is raining, so water may be on the road, and if there is water flowing in the road, the friction will reduce very adversely. So it is desirable that even if there is less or very minimum friction is available, vehicle should pass through the turn. So the banking angle is designed for a particular speed at which no friction is required. Yes, if there is friction, it is an advantage. In absence of friction, the road exerts only the forces of normal reaction on the wheels. All these normal reactions are in the same direction, so can be represented by their resultant. One thing, this way, what we are doing, we are representing the car by a box. No need to show the wheels because we are representing the total normal reaction by a single force. So no need to show all the four wheels. For simplicity, the car is also represented by a square box of mass m as shown in the figure. The forces acting on the car are its weight mg and the normal reaction n. These two forces provide the necessary centripetal force. So what we have in vector form, what you can write here, mg vector plus n vector is equal to mac. Here c stands for centripetal acceleration. You can write n also. But this vector method we can use also, and here we use the analytical method. Say car, normal reaction, weight, angle between mg and normal reaction will be theta, and that will be angle of banking. And these two forces must be equal to man, this way. And coordinate axis, as it is desirable circular motion or curvilinear motion, one axis must be along the normal. So here x is equivalent to normal axis and y is vertical. No need to show the tangential force because vehicle is assumed to move with a constant speed. So there is no tangential acceleration. So no need to show the tangential direction. Now what we can write here, first equation, summation fy is equal to may. For that we had to resolve n into its xy component. So in this way, this angle is theta, this angle will also be theta. So this component will be n sine theta, this component will be n cos theta. So summation fy is equal to m0 because in y direction vehicle has no acceleration. So what you can write here, n cos theta is equal to mg. So this is one equation. Similarly, we can write for normal direction, summation fn is equal to man. What we have, n sine theta is equal to man and an is v square by r. So n sine theta is equal to mv naught square by r. So v naught is what? The specified speed. Now by equating the quotients of the LHS and RHS, we get the desired angle theta. From the above two equations, we get theta is equal to tan inverse v naught square by rg. Now you can see the expression. This expression is similar to the lean angle. And this is the angle of banking desired for that speed. Of course, or you can see in other word, if for this bank angle, this should be the speed. But if friction is available, it will give us advantage. And how the friction will give us advantage, let us see in the next example. Example 9. A curve is banked at angle greater than the angle of repose. If coefficient of static friction between the tires and the road is μs, find the range of speeds a car can have without skidding. Now, what does it mean? Actually, the banking angle is designed assuming there is no friction. But if there will be friction, it will give us advantage. We have a range of speed. And how we can have range of speed? Let us see. A speed v naught obtained in the previous example. No friction is required. At a speed higher than v naught, the car has outward sliding tendency, demanding frictional forces to act inwards. At speeds lower than v naught, the car has inward sliding tendency, demanding frictional forces to act outwards. Now it is very easy to understand. At speed, very high speed, the car will have outward sliding tendency, so friction will act inward. But at a very low speed, the car will have inward sliding tendency because the angle of banking is greater than angle of repose. So car may slip inward, so friction will act outward. So that was the very common idea I have explained here. Now we have maximum safe speed. From this idea, it is very clear. For maximum safe speed, it means that speed is greater than v naught. So friction vehicle has outward sliding tendency and friction force will act inward. And what we can think, more is the speed above v naught, more is the outward sliding tendency and more friction will be required. Greater is the speed above v naught, greater is the outward sliding tendency. The maximum speed limit is decided by the limiting friction acting inwards available to counterbalance the outward sliding tendency. Actually, when the speed will be maximum, the friction will achieve its limiting value, and if we apply this condition, we can find expression for the maximum speed, and for that we have to apply Newton's laws. NLM for the car from the ground frame, inertial frame. So we will draw the free body diagram. In free body diagram, how many forces we have to show? The weight, the normal action and the friction. These are the real forces, and that will be equal to kinetic diagram MAN. So car we are again modeling by a square box. So mg at angle theta, and this theta is angle of banking, normal reaction, and frictional force will be inward. We have seen here because at a higher speed the vehicle has outward sliding tendencies, friction will be inward, and at maximum speed this friction will achieve its limiting value. So it will be equal to MAN, and AN is equal to V max square by R. So we will substitute the value of n wherever desired. Now we have two coordinate axes, one axis along normal, so x is equal to normal, it is y. So according to this coordinates axis, we have to resolve n and fsm into its component. Let us first resolve n. So this angle theta, so this will be n cos theta, this will be n sin theta. Now we have to resolve fsm. So this angle theta, so this component will be what? Fsm cos theta, this will be fsm sin theta. So fsm cos theta and fsm sin theta. Now all the necessary thing we have done, we can write the equation. First summation Fy equal to 0. So Fy equal to 0 means this force plus this force is equal to this force, or this force minus this force equal to this force. So what you write here? N cos theta minus Fsm sin theta is equal to mg. N cos theta is equal to mg plus Fsm sin theta we write here and we bring it on this side. So n cos theta minus Fsm sin theta is equal to mg, equation number 1. Similarly, we can write for that is summation f n is equal to man. For that, what we write here? N sin theta plus Fsm cos theta is equal to man. N sin theta plus Fsm cos theta is equal to man, equation number 2. Now for the further analysis, we have to use only these two equations. I am writing with these two equations. N cos theta minus Fsm sin theta is equal to mg, equation 1. And what was equation 2? N sin theta plus Fsm cos theta is equal to man. And we can replace the value of Fsm. What is Fsm? Mus into n. Substituting Fsm is equal to mus into n in the above equations, what we get? Equation 1 will be converted to n cos theta minus mus into n sin theta. N cos theta minus mus into n sin theta is equal to mg. And equation 2 will become n sin theta plus mus into n cos theta. N sin theta plus mus into n cos theta is equal to man. Now what we can do? Just if you take quotient of the LHS, n will cancel out because we have to eliminate n. So what we do? Ratios of RHS sides and left hand side of the above equations must be equal. So what we have? This upon that is equal to this upon that. So sin theta, this n upon g is equal to sin theta plus mus cos theta upon cos theta minus mus sin theta. So very simple. Now we have to replace the value of an. What is v max square by r? Substituting an is equal to v max square by r, we get v max square is equal to gr. This rg will shift here and take square root. So sin theta plus mus cos theta upon cos theta minus mus sin theta. Very simple expression, but again we can simplify it further. Divide the numerator and denominator by cos theta. So what you get here? Tan theta plus mus upon 1 minus mus tan theta. So we do it here. V max is equal to root gr tan theta plus mus upon 1 minus mus tan theta. Now if you substitute mus is equal to tan phi s, so this will become very simple expression tan a plus b. Substituting mus is equal to tan phi s, what you get? V max is equal to root gr tan theta plus phi s. Why I have converted the relation into that? Because it will be very simple to remember. Here, so many times you will find questions to solve on the banking or similar to banking, some other question similar to banking. So at that time you have to need this expression, but to deduce these expressions whenever it is required is not desirable. But if you remember it, you can use it very easily. So this expression is simple to remember. Now we have to calculate the minimum speed, and for minimum speed we again use the same logic. For a speed lower than v0, the vehicle has inward sliding tendency and friction will act outward, and for the least speed this friction will achieve its limiting value. Minimum safe speed. Lesser is the speed below v0, greater is the inward sliding tendency. The minimum speed limit is decided by the limiting friction acting outwards available to counterbalance this inward sliding tendency. That is very important idea. So when the speed is minimum, the static limiting friction will act outward. Here we have taken the angle of banking is greater than angle of repose. NLM for the car from the ground frame when we are calculating minimum speed. So friction will act what? Outward. We represent the car again by a box and show all the forces, the force mg, and that will make angle theta from the normal, and the normal reaction and friction will act outward as we have seen here, and this will be limiting friction, and this will be equal to the kinetic diagram MAN, and we take the coordinate axis, normal axis and vertical. So x is equal to normal and y axis. Now while writing equation, we have to resolve all the vectors which are not along this axis into components. So we have to resolve FSM and n into their components. So let us do for n first. So this angle will be theta. So this vector will be n cos theta and this will be n sin theta. Similarly for FSM, this will be FSM cos theta and this will be FSM sin theta. Now we can write equation first. Summation Fy is equal to 0 because the car has no acceleration in the y direction. So what we have, n cos theta is equal to mg minus FSM sin theta, or n cos theta plus FSM sin theta is equal to mg. We call it equation 1. Similarly for summation Fn is equal to mn. For this, in normal direction there is 1 for this n sin theta and this f cos theta. So what we have, n sin theta minus FSM cos theta is equal to man. N sin theta minus FSM cos theta is equal to man. Equation number 2. Now what we do, we substitute mu s into n for FSM and then take ratio of right hand side and left hand side, equate them. So what we do, substituting FSM is equal to mu s into n in these equation and then equating ratio of right hand side and LHS side. So ratio of right hand side, what? Equation 2 upon equation 1, En by G. So here En by G, and here what we have, mu s into n was there, so n will cancel. So what we get, sin theta minus mu s cos theta upon cos theta plus mu s sin theta. So An upon G is equal to sin theta minus mu s cos theta upon cos theta plus mu sin theta. Substituting An is equal to V min square by R. See from here. So V min square by R. So here Rg, we bring Rg on that side and take a square root. So what we get, V min is equal to Gr sin theta minus mu s cos theta upon cos theta plus mu sin theta. Again we do the same manipulation. We divide the numerator and denominator by cos theta. So what we get, tan theta minus mu s upon 1 plus mu s tan theta, and substitute for mu s tan phi s and we get simple relation. That is, substituting mu s is equal to tan phi s, what we get, V min is equal to root gr tan theta minus phi s. So here this will help us to remember the result. What? For optimum speed or design speed, you can see what it was, root gr tan theta. For maximum, root gr tan theta plus phi s. For minimum, root gr tan theta minus phi s. And again, just see, these relations you may use, you may have to use several times in several problems. Again, these relations we can very easily deduce by using geometrical method. Let us see what we can do in that. Geometrical method. At the design speed, there is no need of friction and the normal reaction is the total contact force. At the maximum speed, the total contact force makes an angle phi s inwards, and at the minimum allowable speed, the total contact force makes an angle phi s outwards. And these things are very easy to understand because when the speed is higher, vehicle has outward sliding tendency and friction will be inward, so R will tilt inward. And for minimum speed, the vehicle has inward sliding tendency, friction is outward, so R has outward tilt. And for extreme value of this speed, the R will make angle phi s inward for maximum speed, and R will make angle phi s outward for minimum speed, and we'll account for that. But what will be equation? Mg vector plus R vector is equal to Mn vector. NLM from the ground frame, Mg vector plus R vector is equal to Man vector. So we represent it. First we do for the design speed or specified speed where there is no friction. In this case, the normal reaction is the total contact force. So we draw the mg, and the total contact force will be N. This will be along theta, this, and Amn must start from the tail of this vector and go there. So this way. So this will what? Mv naught square by R, and we can directly write from here what? Mv naught square by R is equal to mg tan theta. So design speed, Mv naught square by R is equal to mg tan theta, and you can simply write by cancelling Mv naught is equal to root gr tan theta. Just see how simple the deduction was. Now let us come for the maximum speed. For maximum speed, the R will tilt into the turn here on that side, angle phi s. So this way, this angle phi s, and again this vector must be horizontal. So mv max square must be from this point to that point, and from here to here will be R. So this is R, and this will be what? Mv max square by R. Now you can see again, mv max square by R is equal to mg tan theta plus phi s. We can obtain it without too much mathematical manipulation. So what is maximum speed? Mv max square by R is equal to mg tan theta plus phi s, and by simple manipulation what you can write here, V max is equal to root gr tan theta plus phi s. Similarly, we can proceed for the minimum speed. What we do? When the speed is minimum, the total contact force makes angle phi s outward. So here, this way, here will be your R. So this way, this angle will be phi s, and from this point to that point will be the vector mv min square by R. So this mv min square by R. So now from this triangle, what you can see, mv min square by R is equal to mg tan this angle theta minus phi s. So minimum speed, mv min square by R is equal to mg tan theta minus phi s, and we can write much easily what? V min is equal to rg tan theta minus phi s. Now you can see why I am saying that these relations are very simple to remember in this form. Without friction, rg tan theta. With friction maximum, theta plus phi s. With friction minimum, theta minus phi s. Now, these are the very basic examples on circular motion. Now you are in a position, after carefully studying all these examples and facts, to have enough practice. And for practice, we take first SCB, the chapter for circular motion. Let us decide the homework today. Home assignment. First one, revise all the ideas and examples discussed today in this lecture. That is very important. After you understood all the things, then go the practice problem. Attempt exercise of SCV, chapter 7, circular motion. I ask you to solve all the exercise problem, and in next class, I may take a few more examples on circular motion. Thanks for patient listening. We'll meet in the next class. I am never content until I have conceived a model of what I am studying. If I succeed in making one, I understand. Otherwise, I do not. Sir Lord Kelvin.